In the first section, we were looking at the work done by a force. May not have been very clear there, but we were just focusing on a single force acting on the object. You can define work for each force. There can be 100 different forces acting on the object, and you can find the work for each one of those. However, something very interesting happens. We can get kind of a cool equation out if we look at the work that's done by the net force. If we have the object, it undergoes its displacement. Always seem to draw it kind of going the same way, for better or for worse. And there are several forces acting on the object. Yep, we'll do something here. We have force 1, force 2, force 3. Can have all sorts of forces working. Then we can look at the work that's done by force 1. We can look at the work that's done by force 2, the work done by force 3, and sum those. And in fact, if there are other forces, we can add those in as well. And as long as we take all of the forces into account, this is going to be the work done by the net force given by that. And the work done by the net force, as long as that force is constant, we can still use the earlier definition of work. This would just be the net force times the displacement times the cosine of the angle between the vectors. But something else really good happens when it's the force, or when the work is done by the net force. And actually, we get an equation where the work done by the net force takes calculus to derive this, equals 1/2 times the mass of the object times the final speed of the object squared minus 1/2 times the mass of the object times the initial speed of the object squared. And this is called the work energy theorem. It is valid as long as all of the work goes into the motion of the object, which may sound a little bit strange, but if you're applying forces to an object and it deforms the object, for instance, then not all of that work is going into moving the object. It's doing something else to it. So there are situations where the work energy theorem is not valid. The terms kind of seems to appear mysteriously, but the 1/2 mv final squared, the 1/2 mv initial squared, those have the same form, and in fact that form is very significant, and this is the kinetic energy of an object. Kinetic we did with friction. It just meant the friction involved when an object is in motion. Kinetic means in motion. Kinetic energy is defined to be KE simply 1/2 mv squared. In which case we can take the work energy theorem and actually rewrite it. The net work would be the final kinetic energy minus the initial kinetic energy. But usually when we have a final minus an initial value, we write that as the delta of the value. So this is the change in the kinetic energy. So it's a very shorthand way to write the work energy theorem. But in practice, usually it's going to be the form that appears up here that's most useful to use directly. Nevertheless, work energy theorem, a very useful idea. This is our first energy, so that makes it more significant, even if it kind of is coming out of the blue. Might want to consider the SI unit for kinetic energy. And looking at it, we have a mass times the speed squared. So it looks like the SI unit should be a kilogram times a meter per second squared, but that's a kilogram times a meter squared per second squared. If we want to be a little bit sneaky about it, we can pull one of the meters out. We'd have a kilogram times a meter per second squared times that meter. But the first part of this, kilogram meter per second squared, is actually just the same as a Newton and then times the meter. But that's the same thing as the joule that we introduced in the first section. So the proper SI unit for kinetic energy is the joule. And in fact, the SI unit for any type of energy is the joule. Also introduced in this section, a couple of categories for forces. Let's go ahead and include that. Categories of forces. One way to look at forces would be as conservative and non-conservative. I'll go ahead and tell you up front that a non-conservative force is one that's not conservative. That's easy to say. Anyway, let's look at what a conservative force is. If a force is conservative, the amount of work done by the force is path independent. If the object moves from point A to point B, and we calculate the amount of work that's done by the force of interest, this doesn't have to be the net force, this is just some force acting on the object. But if it goes over some path, so this doesn't have to be the straight displacement straight from A to B. If the path of the object is somewhat complicated, but the force is there acting over it, let's say that this is, well, just the force, I think that works. But the amount of work here over this path is W1. And then we consider a different path. The force is still acting as the object moves from one point to the other. The amount of work here is W2. It does not matter what path is taken, the amount of work is going to be the same in every case. And if that's true, that regardless of the path, the amount of work is the same, then it is a conservative force. Non-conservative force, by contrast, I can do it. Give me half an hour here. Non-conservative force. Yeah, that's one that's not conservative, but that means the work done by the force is path dependent. Since friction converts one kind of energy into heat energy, the path that's taken makes all the difference. If the object takes the long route from A to B, a lot of heat is generated, and that shows that the work that's done along that path will be one value. But if the object goes pretty directly from A to B, the work done there, the amount of heat generated in essence, is going to be very different, and W1 is not going to equal W2. For non-conservative forces, mentioning friction, that's a great example. Another example would be propulsion forces. We talked in class about the plane flying from Greenville to Atlanta. Well, if it flies directly from the one city to the other and then lands immediately, the amount of energy used, the amount of work done by the engines will be one value. But if you go from Greenville to Atlanta and then get stuck in a holding pattern and have to fly around the airport multiple times, the amount of energy that's used, the work that's done by the engines, is going to be a very different value. Going back up to conservative forces, we didn't put in an example, but here's a good one, and that would be gravity. The gravitational force is an example of a conservative force. And having said all of that, here's what's wonderful about conservative forces, and we'll explain this further in the next section, but conservative forces have corresponding potential energies. So if gravity is a conservative force, there's going to be a corresponding gravitational potential energy, and we'll take a look at that in the next video.